Hello students, welcome back to yet another session in this fifth unit, effective temperature chart. So it is a very simple topic. There is a standard chart that is issued by standards, ASHRAE and other standard bureaus. We will see that chart and we will wind up this topic, students. This is the fifth topic in our unit number 5. So these are the topics we have completed so far, and now we are starting the effective temperature and chart. So in next class we are going to see summer and winter load calculations. So factors affecting human comfort is normally in designing winter or summer air conditioning systems, the designer should be well conversant with the number of factors which psychologically affect human comfort. The important factors are as follows. The first one is effective temperature. So this is what we are going to see in this session. And next, heat production and regulation in human body, and we have seen about it in earlier session how the heat is generated through human body and how it impacts the indoor air quality system. Heat and moisture losses from the human body, and this also we have seen in earlier session. Moisture content in air already we have seen in the earlier unit number 4. And the quality and quantity of air motion, hot and cold surfaces, air stratification. So all these topics already we have covered in our earlier sessions, and effective temperature we discussed in this session. So effective temperature here, the degree of warmth or cold felt by human body depends mainly on the following three factors. The first one is dry bulb temperature, relative humidity and air velocity. These are the three main factors we have to consider, and in order to evaluate the combined effect of these factors, the term effective temperature is employed. It is defined as that index which correlates the combined effects of air temperature, relative humidity, and air velocity on the human body. So this simple definition given here for effective temperature, and now it is as simple as this. It is defined as that index which correlates the combined effects of air temperature, relative humidity, and air velocity on the human body. So this is a simple definition. You can write in your own words also. The numerical value of effective temperature is made equal to the temperature of still, so that is 5 to 8 meters per minute air velocity, saturated air, which produces the same sensation of warmth or coolness as produced under the given conditions. So the practical application of the concept of effective temperature is presented by the comfort chart as shown in figure. So that we are going to discuss in next slide. I am going to show you in next slide. So this chart. So this chart is the result of research made on different kinds of people subjected to wide range of environmental temperature, relative humidity and air movement by the American Society of Heating, Refrigeration and Air Conditioning Engineers. So that is ASHRAE. So this is it is came out of different research and done on different persons and different environments, and that is the in short we are studying here. So effective temperature is a comfort chart for still air. It is 8 to 5 meters per minute, and this is the comfort chart. And you can see here this zone is the comfort zone, and this is having the maximum wet bulb temperature of lesser than 20 degree Celsius, and we have the maximum dry bulb temperature lesser than 26 degrees Celsius. So this is the comfort zone, and actually it starts from 19 degree or 17 degree onwards in terms of dry bulb temperature. And we have other lines like relative humidity lines, and this is the summer season, and this is the summer season. And for that, how the curve is drawn, and this is simple comfort chart. And the x-axis dry bulb temperature and y-axis wet bulb temperature, it shows summer and winter season comfort zones. And effective temperature lines, that is inclined, the effective temperature lines are inclined lines. So these are the inclined lines. So these are the inclined lines. So these are known as effective temperature lines. So this is summer season and this is winter season, and now the inclined lines are passing through all three seasons. And we have RH lines and comfort zone indicated centrally. So this is the hashed portion is known as comfort zone. So now it is applicable to reasonably still air. So that is 5 to 8 meters per minute air velocity to situations where the occupants are seated at rest, are doing light work, and to spaces whose enclosing surfaces are at a mean temperature equal to the air dry bulb temperature. So in the comfort chart, so that's what we have seen in earlier slide. So the dry bulb temperature is taken as abscissa and the wet bulb temperature as ordinate. So the relative humidity, that is RH lines, are replotted from psychrometric chart. So psychrometric chart is taken into account here. The statistically prepared graphs corresponding to summer and winter season are also superimposed. These graphs have effective temperature scale as abscissa and percentage of people feeling comfortable as ordinate. So a close study of the chart reveals that the several combinations of wet and dry bulb temperatures with the different relative humidities will produce the same effective temperature. So for example, from the comfort chart we see that for a point corresponding to dry bulb temperature of 17.5 degrees Celsius, wet bulb temperature of 12.5 degree Celsius, the and relative humidity 60%, the effective temperature is 16 degree Celsius. Now for the same feeling of comfort and warmth, there is another point on 100% relative humidity line at which the dry bulb and wet bulb temperature are both equal to 16 degrees Celsius. Thus, both have effective temperature of 16 degrees Celsius again. So, this is the comfort chart and comfort of warmth and the warmth and comfort. So, both conditions are considered here. So observations from the comfort chart, however, all points located on a given effective temperature line do not indicate conditions of equal comfort or discomfort. So extremely high or low relative humidities may produce conditions of discomfort regardless of the existent effective temperature. The most desirable relative humidity range lies between 30 percentage to 70 percentage, and below 30 percentage mucous membranes and skin surface becomes too dry, and above 70 percentage clammy or sticky sensation may develop on the skin. So the curves at the top and bottom of the comfort chart, that's what we have seen, indicate the percentages of person participating in tests who found various effective temperatures satisfactory for comfort. The comfort chart shows summer conditions maximum 98 percentage feel comfortable at 21.6 degrees Celsius. Winter conditions 97.7 percentage desired effective temperature of 20 degrees Celsius. It is found that women require zero point 0.5 degrees Celsius higher effective temperature than men. So it is found by research only. So persons below 40 years of age prefer zero point 0.5 degrees Celsius higher effective temperature than persons below 40 years age. So limitations of the comfort chart, it does not consider variations in comfort due to wide variations of mean radiant temperature, that is MRT, and at 26.5 degrees Celsius a rise of zero point 0.5 degrees Celsius in MRT rises effective temperature by zero point 0.5 degrees Celsius. So MRT influence is less pronounced at low temperatures. So workplace considerations are comfort conditions at work vary with rate of work, amount of clothing, and greater the activity level, lower the effective temperature required. So this is the chart variation of effective temperature with air velocity. So here the dry bulb temperature and wet bulb temperature and velocity of air in terms of meter per minute. So it ranges from 0 to 50, 150 and 210. So this velocity is also taken into account for establishing the comfort zone. So conditions 24 degrees Celsius dry bulb, 16-degree wet bulb, 21 degrees Celsius effective temperature at still air 6 meters per minute. So same condition 17 degrees Celsius effective temperature at 210 meters per minute air velocity, and the trend is followed like this, and same effective temperature is observed at higher dry and wet bulb temperatures with higher air velocities. The reverse occurs at 37.8 degrees Celsius. Higher velocities increased sensible heat, and it is resulting in decreased comfort. So same effective temperature, same feeling of warmth, but does not imply same comfort. And this is the conclusion from chart. And we have modified comfort chart also. So this is the modified comfort chart, and here the comfort chart in figure earlier slide is now obsolete due to these reasons: over exaggeration of humidity at lower temperatures and under underestimation of humidity at heat tolerance level. So these are the two reasons. That is why the earlier slide, the whatever diagram comfort chart we have seen, that is almost obsolete, and this is the new one and the latest one, and this is known as modified comfort chart, and here developed based on ASHRAE standards and based on 1963 research by Institution of Environmental Research at Kansas State University, and assumptions are made here: mean radiant temperature equal to dry bulb temperature, and air velocity is lesser than 0.17 meters per second. And here you can see the specific humidity is considered, enthalpy, vapor pressure, and we have enthalpy. So this is almost like a psychrometric chart only, and comfort zone is now drawn here within this range of all these values: enthalpy, vapor pressure, and of enthalpy here. So using specific humidity, dry bulb temperature, everything is considered, and this is the comfort zone drawn here on the modified comfort chart. So this is the modified comfort chart, and there ends this topic, and we are going to see the summer and winter load calculations in our next session, students. And references, you can refer these books. You can refer R.S. Kurmi for this topic particularly. I have taken from R.S. Kurmi only. So please refer R.S. Kurmi book. Apart from that, we have online resources. You can refer these online resources also. So also you can refer R.K. Rajput, C.P. Arora books. They are also very good books. And but I have taken from R.S. Kurmi book only. Thank you, students. We stop here. We will meet again in next session where we are going to see the calculations of summer and winter load, about load. So that we are going to commence in next session. Thank you, students. We stop here. We meet again in next session.